Our third and final case is where the characteristic polynomial has repeated roots. So I'm going to reframe this equation just a little bit. I'm going to divide by m, and I'm going to write it as x double prime plus 2ax prime plus a squared x is equal to 0. So in this case, I'm thinking about a as being b over 2m. And so that means that the a squared will exactly balance this out so that we only get one root. So let's look again at the characteristic polynomial for this equation. So if I was to plug in my solution, e to the lambda t, the characteristic polynomial would be lambda squared plus 2a lambda plus a squared is equal to 0. I can factor that polynomial so that lambda plus a squared is equal to 0. And that's going to tell me that lambda is going to equal minus a. So that gives me one solution to this problem. It's e to the minus at. But I need a second linearly independent solution. I need to figure out some other solution to this problem that will be linearly independent from e to the minus at so that I can span the entire space. Well, how do I find that? Well, I'm going to use a technique called reduction of order. We're going to assume that the second solution looks like a function maybe v of t times the first solution x1 of t. So we're essentially saying that the second solution will have an e to the minus at in it, but it'll be multiplied by some other function of t. So is that going to be reasonable as a guess? So the first question is will x1 and x2 in this case be linearly independent? Let's see. So we're going to take the Wronskian to figure that out. So w of x1, x2 is going to be the determinant of the matrix, let's see, x1. x2 we're going to call vx1. And then the derivative of x1 is x1 prime. But the derivative of vx1 is going to be v prime x1 plus vx1 prime. So I'm going to take that determinant. That's going to tell me that x1 times v prime x1 plus v x1, sorry, let me rewrite that, plus x1 v x1 prime minus x1 prime vx1 is the determinant. There's a prime on the end there, okay? And so the second two terms actually cancel. They're equal and opposite. And so I essentially am going to get x1 squared v prime. Now, is that going to be 0? Well, x1 is not 0. 0 cannot be our solution here. Okay, so x1 is not 0. So this is not equal to 0 as long as v prime is not equal to 0. Well, what would it mean if v prime was 0? What that would mean is that v is a constant. Well, if v was a constant, then x2 would just be a constant multiple of x1, and of course it would not be linearly independent. So as long as our v is not constant, then x2 will be linearly independent from x1. Okay, now what we're going to do is we're going to substitute x2 into our differential equation for v of t. Okay, so essentially, and I'm going to use the space here, I'm going to know that x2 is going to be v times x1. x2 prime, the derivative, is going to be v prime x1 plus v x1 prime. And then x2 double prime, okay, the second derivative, I'm going to take the derivative of the derivative, is going to be v double prime x1 plus v prime x1 prime. And then that's just coming from the first term. From the second term, I get another v prime x1 prime. And then finally, v x1 double prime. And now I'm going to plug that into my differential equation. So here I'm going to see that I have that my differential equation x double prime plus 2ax prime plus a squared x is going to equal, okay, the second derivative comes first, so v double prime x1 plus 2v prime x1 prime plus v x1 double prime plus 2a times x prime, so that's going to be v prime x1 plus v x1 prime plus, and then I'm going to have a squared times x, which is v times x1. Okay. So, of course, that I'm going to set equal to 0. So 0 in this case is going to equal, now I need to kind of rearrange things. So I'm going to call this v double prime x1 plus 2v prime x1 prime. So nothing has changed there. And then I'm going to pull out a plus 2a v prime x1. So let me just underline these things real quick. So I'm going to get this one, and this one from this one, and that one. Okay, then I have a v times x1 double prime plus a v times 2a x1 prime plus a v times a squared x1. So in this case, let me use a different color here. So I've got this term, and this term end up here. Now, x1 double prime plus 2a x1 prime plus a squared x1, that is 0 because x1 solves our first equation. So what I'm left with is just what's underlined in red. And now I'm going to actually write out what some of these things are. So this is going to be v1 double prime, x1 is e to the minus at, plus 2a v prime e to the minus, 2v prime times x1 prime, so that's a e to the minus at, plus I've still made a mistake here, sorry. So x1 prime is minus a e to the minus at, much better, plus, and then 2a v prime x1 is just e to the minus at. Now, hopefully we'll notice that the 2v prime minus a e to the minus at cancels with the 2av prime e to the minus at. So we get this and this cancel. Just don't want to write through that negative sign there. Okay, so in fact, maybe I'll use a different color here. So this one cancels with that one. So that tells me, well, e to the minus at is never 0. So that tells me that v double prime must equal 0. So what function has a second derivative that's 0? That function is going to be v of t equals a linear function, c1 plus c2 times t. Now, I don't need the c1 part because I'm going to multiply this function by x1. And because I'm going to multiply this function by x1, that tells me that this will just give me a constant multiple of x1. So I don't need that part. So I only need the constant multiples of t times x1. So in fact, it's easiest, any v of t in this form will work, but I'm going to choose that v of t just be t. I don't need the constant part. I just need a t, and I don't need the constant in front of t because that will come out in my general solution. So my two linearly independent solutions are going to be e to the minus at and t e to the minus at. And you can check that they're linearly independent, again, by taking the Wronskian, although we know that they will be because v of t was not constant. So the general solution looks like c1 e to the minus at plus c2 t e to the minus at. Okay, so let's sketch what the solution will look like in this case. Again, I have t and x. And if I start at some point, we'll call that maybe x0, then what I get is something that will decay faster than my underdamped oscillator did. And that's because that in my underdamped oscillator, I had two different exponential decays. One was slower and one was faster. And in this case, I only have one, the faster exponential decay. So this oscillator is called critically damped. So it's critically damped because there's just the right amount of friction on the system so that if I pull back on my mass on a spring, that it'll snap back into place as quickly as possible. It'll just go right back into position. It won't oscillate like the underdamped oscillator. It won't go slow like the overdamped oscillator. It's just going to push right back into position. Imagine having a door that has some sort of friction on it. You open it, and when you release the door, it just slams back shut. That's going to be the critically damped oscillator. So let's look at 3 example problems. And I want to show you kind of how quickly and easily you can solve these problems. Now, I've been doing x of t this whole time, but my examples here are actually in y of t, and that is okay. We can use the function x of t if we're thinking about a horizontal oscillation, y of t for maybe a vertical oscillation. So when I want to find the general solution for, say, a differential equation y double prime plus 3y prime plus 2y equals 0, the first thing that I want to do, and I'll just kind of show you how this works, is I want to substitute in e to the lambda t. Now I'm going to do this one time so that we get used to kind of, this is the idea of the process. Okay, so if I substitute e to the lambda t, the second derivative is lambda squared e to the lambda t plus 3 lambda e to the lambda t plus 2 e to the lambda t equals 0. And then I can just look at the characteristic polynomial, kind of removing the lambda to the t's, is lambda squared plus 3 lambda plus 2 equals 0. So I can factor that. Lambda plus 1 times lambda plus 2 equals 0. So that tells me that lambda could be -1 or -2. So I have a general solution. And that general solution is y of t equals c1 e to the minus t plus c2 e to the minus 2t. So this one is going to be overdamped, 2 real roots. Now we can do the same thing with, say, this second order equation. Again, we could substitute y equals e to the lambda t so that we have a second derivative of lambda squared e to the lambda t plus 4 lambda e to the lambda t plus 9 e to the lambda t is equal to 0. I can factor out the e to the lambda t, which tells me that lambda squared plus 4 lambda plus 9 must equal 0, because e to the lambda t is not going to be 0 everywhere. That is going to be my characteristic polynomial. And then finally, I'm going to get that lambda is going to equal -4 plus or minus the square root, because I could not factor, of 16 minus 4 times 9 over 2. And that becomes -2 plus or minus I square root of 5 if I simplify. That gives me a general solution. And that general solution is going to be y of t is equal to the real part here, so c1 e to the minus 2t cosine of the imaginary part, square root of 5t, plus c2 e to the minus 2t sine of square root of 5t. So again, I'm just reading off the forms of the general solution that we got from solving these problems throughout these notes. Okay, so that's going to be an underdamped oscillator. Okay, so let's do this one more time. We're going to substitute y equals e to the lambda t. That's going to give me lambda squared e to the lambda t plus 4 lambda e to the lambda t plus 4 e to the lambda t, kind of substituting in derivatives, equal to 0. So that's going to give me the characteristic polynomial of lambda squared plus 4 lambda plus 4 equals 0. Notice that the coefficients, are the coefficients of y double prime, y prime, and y. And so if you want to skip the substituting step and just go right to the characteristic polynomial, I don't blame you. You can do that. This factors to lambda plus 2 squared equals 0. And so lambda is a repeated root of -2. So my general solution is going to be y of t equals c1 e to the minus 2t plus c2 t e to the minus 2t. That is a critically damped oscillator. And so there's examples of all three types. I'd like to quickly plot these solutions so you can kind of see what's going on. So we're going to go into slopes. This is the oscillations activity in slopes. I have set up the first equation, which was y double prime plus 3y plus y prime plus 2y is equal to 0. And as you can see, plotting it, that's going to be an overdamped oscillator. In fact, we can look at what happens with the mass on the spring by pushing play. The spring is displaced, and then it slowly moves down back into place. That's opposed to, say, the underdamped oscillator. So that's when I had B, my frictional constant, being 4, and K, my spring constant, being 9. Okay, and that has a little bit of oscillation to it, not a lot, but we put it into position and then see it kind of oscillates just a little bit. I think the oscillation might be a little bit more clear if I zoom this way a little bit. So we're going to push play, and at least we can see a little bit of that oscillation. Okay, it's not that much oscillation, but just a little bit. Okay, finally, let's look at the critically damped oscillator. That was when I had a 4 for the coefficient of friction and then 4 for the spring constant. Okay, and notice that this one's going to kind of return back to normal a little bit more quickly. Well, if I put it on the same scale as the other one, then it will return more quickly. So snaps right back into place. Now, what I hope you see is that the critically damped oscillator, right, is a point right there between the overdamped oscillator and the underdamped oscillator. You have to have just the right amount of friction on this oscillator to make it critically damped. If I decrease the friction just a little bit, notice that I get an oscillation immediately, just a little bit of decrease from 4 creates an oscillation, okay? And then I end up with an underdamped oscillator. Let me play this one for you so that you can get a good sense of what the underdamped oscillator does. Okay, so it oscillates back and forth. Okay, but if I move the friction above 4, it goes from being critically damped to overdamped, and that means it's going to approach the equilibrium much more slowly. And those are the examples of the 3 types of oscillations with damping.